3 minutes ago is not where this story begins. The real beginning happened quietly, before the headlines, before the speculation, and before most astronomers even knew there was something unusual moving through our solar system. 10 days before the object was officially announced, one of the most powerful new observatories on Earth had already photographed it by accident. Then, weeks later, the James Webb Space Telescope pointed directly at the same visitor and found a chemical signature unlike anything scientists had measured in a comet before. Two telescopes, two completely different missions, one object from beyond our solar system. And by the end of this video, you will understand why that combination turned a strange discovery into one of the most extraordinary astronomical stories of the decade. On July 1st, 2025, the Atlas survey in Chile detected a fast-moving object crossing the sky. At first, it received the technical designation C/2025N1, the kind of name that sounds ordinary because astronomers assign labels like this to newly discovered comets and minor bodies all the time. But the orbit immediately stood out. The object was not circling the sun in a closed path. It was moving on an open, hyperbolic trajectory, which meant it had entered our solar system from interstellar space and would eventually leave again. Astronomers soon renamed it 3I/Atlas. The 3I mattered. It meant this was only the third confirmed interstellar object ever observed passing through our planetary neighborhood. That alone would have made it important. But the first major twist came when scientists at the Vera C. Rubin Observatory went back through older images. Rubin was still in its testing and science validation phase. Its teams had been checking cameras, calibration systems, image quality, and software. They were not specifically searching for an interstellar comet. Yet when researchers reviewed those earlier observations, they found 3I/Atlas sitting inside them. Rubin had photographed the object on June 21st, 2025, 10 full days before the official discovery announcement. The telescope had seen the visitor before humanity realized what it was. Think about that for a moment. An ancient object traveling through the galaxy for billions of years crossed into the part of the sky being tested by a brand new observatory at exactly the right time. Nobody commanded Rubin to track it. Nobody knew it was there. The telescope simply happened to be looking in the correct direction, and it did not capture the object once. Rubin continued recording it repeatedly, gathering dozens of exposures that would later become some of the earliest high-resolution observations of the object available anywhere. When scientists examined those images, they saw the comet changing. A cloud of gas and dust called a coma was forming around the nucleus and growing as the object moved closer to the sun. That part was expected. Comets heat up as they approach the sun. Frozen material begins turning directly into gas, lifting dust away from the surface and creating the glowing cloud we recognize as a coma. But one feature immediately looked strange. A dust structure appeared to extend toward the sun rather than away from it. That sounds wrong because the classic image of a comet shows a tail streaming away from the sun. Solar radiation and the solar wind normally push material outward, creating a tail that points in the opposite direction. A sunward-pointing feature is unusual enough to attract attention, and naturally it became one of the details people online started using to make the object sound mysterious or even artificial. But unusual does not mean impossible. Astronomers have seen sunward-facing dust structures before. Depending on particle size, viewing angle, and uneven material released from the surface, a comet can produce a feature that appears to point toward the sun. So Rubin had already given scientists two valuable things: an early timeline and a detailed record of the comet's changing appearance. But Rubin could not answer the biggest question: what was this object actually made of? That required a very different kind of instrument. Enter the James Webb Space Telescope. Rubin is designed to survey enormous areas of the sky quickly. Webb is designed to stare deeply at selected targets and separate their light into incredibly detailed spectra. In simple terms, Rubin can tell astronomers where something is, how bright it is, how it moves, and how its visible appearance changes. Webb can take the light coming from that object and break it apart to identify molecules and chemical fingerprints. One telescope is built for discovery and coverage. The other is built for forensic analysis. When Webb observed 3I/Atlas with its near-infrared spectrograph, the object stopped being just a moving point surrounded by dust. Its chemistry began to come into focus. Scientists detected carbon dioxide, water, water ice, carbon monoxide, and carbonyl sulfide in the coma. None of those ingredients by themselves were shocking. Comets in our own solar system contain many of the same substances. What surprised researchers was the balance between them. The ratio of carbon dioxide to water was exceptionally high, reportedly higher than scientists had measured in any other comet they had studied. That ratio matters because comets are time capsules. Their frozen material preserves information about the environment where they formed. Temperature, radiation, distance from a star, and the chemical makeup of the surrounding gas can all influence which compounds become trapped in the ice. So when astronomers measure unusual ratios inside a comet, they are not just cataloging ingredients, they are reading clues about a birthplace that may no longer exist, and 3I/Atlas did not form here. Its orbit already proved that. But Webb's chemical evidence pushed the story much further. Later observations of the comet, especially after it had passed through the warmer inner part of the solar system, allowed scientists to study isotopic ratios involving carbon and deuterium, a heavier form of hydrogen. Those ratios can preserve information about the conditions under which ancient ice formed. According to the scientific interpretation described in the research, the signature pointed to an origin billions of years before our own solar system existed. The estimate was staggering, roughly 10 to 12 billion years old. Our sun is about 4.6 billion years old. Earth is about the same age. If that estimate is correct, the ice inside 3I/Atlas may have formed more than twice as long ago as the birth of our solar system. The object could contain frozen material assembled during a much earlier era of the Milky Way, when the galaxy itself had a different chemical history, and generations of stars had not yet enriched space with the same mixture of elements we see today. This is where the word terrifying in the headlines becomes almost misleading, because the truth is not frightening in the ordinary sense. It is unsettling in scale. We are talking about a piece of matter that may have existed for most of cosmic history, wandering through interstellar darkness long before Earth, long before the sun, and long before any human being could have imagined a telescope, and then it crossed our neighborhood at the exact moment we had instruments capable of recognizing what it was. That coincidence is one reason the story spread so quickly. Another reason is the history of interstellar objects. Before 3I/Atlas, only two had been confirmed. The first was Oumuamua in 2017. It became famous because of its unusual shape and a small non-gravitational acceleration detected as it left the solar system. That acceleration inspired years of speculation, including claims that the object might be artificial. Most astronomers favored natural explanations, but the mystery made Oumuamua a cultural phenomenon. The second interstellar visitor was 2I/Borisov in 2019. Borisov looked and behaved much more like a familiar comet. It had a visible coma and tail, and scientists could compare its chemistry more directly with comets formed around our own sun. 3I/Atlas became the third entry in this tiny list, but it arrived at a different technological moment. This time, humanity had Webb, it had Hubble, it had Rubin, it had SPHEREX, and other spacecraft and observatories capable of examining the same object in different ways. That gave scientists something they did not have with Oumuamua: time, coverage, and multiple instruments working together. Its speed reinforced that conclusion. As it moved through the inner solar system, the comet was traveling at roughly 137,000 miles per hour, or about 221,000 kilometers per hour. At that velocity, the sun could bend the path, but it could not capture the object permanently. 3I/Atlas was always going to leave. That creates one of the strangest parts of the story. Astronomers may never see this object again. After billions of years drifting through the Milky Way, it entered our solar system, passed the sun, crossed within observational range of Earth, revealed its chemistry to our telescopes, and then continued outward. There is no return orbit. There is no second chance centuries from now. Once it becomes too faint, the encounter is over. Yet before that happened, scientists mobilized an extraordinary network of instruments. Each instrument saw a different version of the same traveler. Rubin saw its position and activity over time. Hubble helped constrain its physical scale. Webb read its chemistry. SPHEREX examined additional infrared signatures. TESS contributed time series observations. JUICE added a view from a spacecraft on an entirely different mission. Instead of one telescope making one dramatic discovery, the real story became a coordinated reconstruction of an object that had no intention of staying long enough for us to understand it. That is also why the pairing of James Webb and Vera Rubin is so powerful in a title. Their roles are almost opposites. Rubin is a wide field hunter. Webb is a precision investigator. Rubin watches enormous pieces of sky and catches things nobody planned to find. Webb focuses on individual targets and extracts hidden information from their light. One answers, "What just appeared?" The other answers, what is it? With 3I/Atlas, those two abilities overlapped perfectly. Rubin's archive pushed the observational history backward by 10 days. That may sound minor, but in comet science, early observations matter. Every additional measurement improves the orbit. Every image provides another data point for how brightness and activity evolve. Every earlier exposure lets researchers reconstruct what the object was doing before intense solar heating changed its surface. Webb, meanwhile, supplied the deeper chemical evidence. The unusually high carbon dioxide to water ratio suggested the object formed under conditions different from many comets we know. The isotopic measurements pushed scientists toward an even more dramatic possibility that the material originated during an early stage of the Milky Way's evolution. This is the point where sensational versions of the story often jump to the word alien, so we need to separate two very different meanings of that word. Is 3I/Atlas alien in the literal sense that it came from beyond our solar system? Yes. It is extraterrestrial material from another stellar environment. Is there evidence that it is an alien spacecraft, engineered probe, or artificial object? No. The observations described so far support a natural comet. The coma grows as sunlight heats the surface. The gas and dust are consistent with known cometary materials. The trajectory follows gravity. Small changes can be explained by ordinary outgassing, where jets of material escaping the nucleus create tiny forces. The unusual tail geometry has physical explanations. The chemistry is strange in ratio, not in ingredient. Nothing requires technology to explain it, and that may actually make the discovery more important. An artificial probe would be astonishing, but an ancient natural object gives astronomers something they almost never receive: a physical sample from another region and another era of the galaxy. We cannot fly a spacecraft 10 billion years into the past. We cannot travel across thousands of light years to scoop ice from a distant planetary system, but sometimes the galaxy sends material to us. 3I/Atlas is like a sealed package that survived an impossible journey. Imagine finding a bottle on a beach that had crossed an ocean for thousands of years. Now replace the ocean with interstellar space, replace the bottle with a comet, and replace thousands of years with billions. The object did not carry a written message. Its message was its chemistry. The molecules trapped in its ice preserve the conditions of a place and time we may never observe directly. Deuterium is especially important in that kind of analysis. A normal hydrogen atom has one proton. Deuterium contains a proton and a neutron, making it heavier. The ratio between ordinary hydrogen and deuterium in water or other molecules can vary depending on the environment where those molecules formed. Extremely cold conditions, radiation history, and the chemistry of the surrounding cloud can leave a lasting isotopic signature. Astronomers use those signatures like historians use handwriting or archaeologists use layers of sediment. They are not perfect clocks, but they can help distinguish material formed under different cosmic conditions. Carbon isotopes can offer another layer. The Milky Way did not begin with its present mixture of elements. Early generations of stars formed, lived, and exploded, releasing heavier elements into space. Later stars and planetary systems formed from increasingly enriched material. This gradual process is called galactic chemical evolution. An object formed very early can therefore carry a slightly different fingerprint from one formed around a younger star much later. That is why the age estimate attached to 3I/Atlas is so dramatic. If the comet really formed 10 to 12 billion years ago, it may preserve chemistry from a period when the Milky Way was still young. It is not simply older than Earth. It may be older than the majority of familiar structures in our solar neighborhood. The speed of its journey is equally difficult to imagine. Even at more than 200,000 kilometers per hour, interstellar space is so vast that traveling between stars can take enormous stretches of time. Researchers studying its motion have suggested the object may have spent billions of years wandering between stellar systems. Statistical analyses even imply it may not have passed particularly close to another star during much of that journey. For most of its existence, nothing happened. No planet observed it, no telescope tracked it, no atmosphere heated it. It simply moved through darkness. Then, for a brief moment, it met the sun. That encounter changed the comet physically. Solar heat began releasing gases that had been frozen for immense periods. Dust lifted from the surface, the coma expanded, the object brightened. Features developed that made it visible to instruments across the solar system. Material that may have remained locked away since the early Milky Way was suddenly exposed to sunlight from our star, and we were watching. This is the deeper reason Rubin's accidental prediscovery matters. Modern astronomy is becoming less dependent on knowing where to look in advance. For most of history, telescopes were pointed at specific targets chosen by humans, but survey observatories changed that model. Rubin's legacy survey of space and time is designed to repeatedly scan huge portions of the sky over many years. It does not need to know that something unusual is coming. It just needs to keep looking. That creates a kind of astronomical memory. When a new object is discovered, scientists can search backward through previous images and ask, was it already there? In the case of 3I/Atlas, the answer was yes. The object had been hiding in plain sight inside test data. As Rubin's full survey continues, similar pre-discoveries may become routine. Asteroids, supernova, variable stars, and future interstellar visitors could all be recorded before anyone realizes they are important. Webb represents the second half of that future. A survey telescope can find the needle. Webb can examine the needle atom by atom. Because Webb operates far from Earth and is optimized for infrared astronomy, it can detect faint molecular signatures that ground-based telescopes may struggle to isolate. For a cold, distant comet, that capability is invaluable. Infrared spectroscopy reveals gases and ices that do not announce themselves clearly in ordinary visible light. So the combination becomes incredibly powerful. Rubin catches the unexpected. Webb explains it. That is why 3I/Atlas may be remembered not only for what it is, but for when it arrived. It appeared during a transition in astronomy at the moment wide-field automated surveys and extremely sensitive space telescopes began operating together. The object may have been ancient, but the way humanity studied it was completely modern. And there is another reason this matters. 3 confirmed interstellar objects in less than a decade suggest that the galaxy may be full of debris moving between star systems. Every planetary system forms from disks of gas, dust, rock, and ice. During the chaotic early stages of planet formation, gravitational encounters can eject enormous numbers of smaller bodies. Some may wander through interstellar space indefinitely. If Rubin discovers more of them, astronomers could eventually compare entire populations. One interstellar comet tells us about one distant environment. 10 could reveal patterns. 100 could begin to show how planetary systems across the galaxy differ from our own. Do they contain more carbon dioxide, different water chemistry, different isotope ratios? Are some unusually rich in organic molecules? Do older objects differ systematically from younger ones? How often are rocky interstellar bodies ejected compared with icy ones? Those are questions that cannot be answered from 3I/Atlas alone. But this object proves the method works. We can find these visitors, we can photograph them early, we can measure their orbits, we can study their gases, we can compare their chemistry with objects born around our own sun, and if we are lucky, we can do all of that before they disappear forever. Right now, 3I/Atlas is already on the outbound leg of its journey. It has passed its closest region to the sun and Earth and is fading as it moves back into deep space. The gases will weaken as the surface cools. The coma will become harder to detect. Eventually, even our most powerful instruments will lose it against the darkness. But the data will remain. Dozens of Rubin images, spectra from Webb, measurements from Hubble, SPHEREX, and other observatories, orbital calculations, chemical ratios, brightness curves, dust models. Every observation becomes part of a permanent scientific record of a visitor that was here only briefly. And that brings us back to the claim that 2 of the world's most powerful telescopes confirmed the same terrifying object. They did observe the same object, but what they confirmed is more interesting than the phrase suggests. Rubin confirmed that the visitor had been in our data before we knew to search for it. Webb confirmed that its chemistry carried a history unlike the familiar comets of our solar system. Together, the observations reveal an object born somewhere else, under different conditions, possibly in a much earlier Milky Way, that happened to cross our neighborhood once and only once. The terrifying part is not that it is coming for us, it is that the universe is so old, so large, and so full of wandering material that something can travel for billions of years and pass through our solar system almost unnoticed. The terrifying part is understanding that the tiny frozen body in these images may have existed before the sun, before Earth, before the planets, and before most of the stars you see when you look up at night. And perhaps the most astonishing part is that we were ready when this one arrived. Not because anyone predicted it, not because a mission was launched to intercept it, but because one telescope happened to be watching, another was powerful enough to interrogate its light, and an entire network of observatories around the world reacted before the opportunity vanished. But for a brief period, the object gave us access to material from beyond our own solar system. That is not a rumor. That is not a science fiction plot. That is the real significance of an interstellar comet, and it changes the way we should think about future discoveries. The next visitor could be smaller, it could be larger, it could move faster, it could contain chemistry even more different from anything we have seen. Rubin may detect it weeks before older surveys would have noticed it. Webb may be able to examine it while it is still far from the sun before heating alters the surface. Other telescopes may add radar, ultraviolet, X-ray, or thermal observations. Each new interstellar object will be another piece of a galactic puzzle. For centuries, astronomy was mostly about studying light that traveled to us. Now, occasionally, the material itself comes here. A fragment of another system enters our neighborhood. We measure it. We watch it change. We decode what its atoms remember. Then it leaves. That is what makes 3I/Atlas extraordinary. Not that it broke the laws of physics, not that it behaved like a spacecraft, not that it threatened Earth, but that a natural object from another part of the galaxy arrived carrying information older than our world, and two of the most advanced observatories ever built were able to read different chapters of the same story. Rubin saw the beginning before anyone knew the story had started. Webb read the chemical ending written inside the ice, and together they turned a faint moving object into a glimpse of the Milky Way's ancient past. So when you see headlines calling this object impossible, terrifying, or unexplained, remember what the real mystery actually is. The mystery is not whether 3I/Atlas is alien technology. The evidence described by astronomers points strongly toward a natural comet. The real mystery is where exactly it formed, how long it wandered, what star system expelled it, and how many more objects like it are moving through the galaxy right now. Those questions remain open, and Rubin has only just begun watching. If its 10-year survey performs the way astronomers expect, this may not be the last interstellar visitor we see. It may be the first example of a new era in which objects from other star systems stop being once-in-a-generation surprises and become a new field of astronomy. When that happens, the biggest discovery may not be one terrifying object. It may be realizing how common these strangers have been all along. For now, 3I/Atlas continues its one-way journey outward, carrying the rest of its secrets with it. But the small fraction it revealed has already given scientists something priceless, a direct chemical glimpse of material that formed beyond our sun, possibly billions of years before our solar system existed. A telescope in Chile saw it before anyone knew its name. A telescope in deep space read the molecules inside it, and for one brief moment, humanity caught a traveler from another part of the galaxy passing through. That is the story worth paying attention to. If you want more fact-based breakdowns of discoveries like this, subscribe and turn on notifications. New telescopes are changing how quickly astronomers can find unusual objects, and the next interstellar visitor may already be somewhere in the sky, too faint for most people to notice, waiting for the right instrument to catch it. And before you go, tell me in the comments which part is the hardest to wrap your head around. That Rubin photographed 3I/Atlas 10 days before its official discovery, that Webb found an extreme chemical signature, that the material may be 10 to 12 billion years old, or that after this one brief encounter, the object is leaving our solar system forever.